In today's video, we will be discussing relations. So, what are relations? Relation is the relationship between elements of two sets where X is related to Y. Here is an example to help you further understand. R is the relation of what the people eat. We understand that Ali, Chong, Kumara, and Tasha ate cookie and pizza but not sushi. Here are some of the properties of relations. First, we have reflexive. The elements of a reflexive relation always relates to itself. Well, take it like when you're walking towards a mirror and you see a reflection of yourself. Next, we have irreflexive relation. As its name suggests, irreflexive relations elements do not relate to itself. Here are a couple examples for you to differentiate reflexive and irreflexive relations. Next, we have transitive. For all elements of X, Y, and Z, if X relates to Y and Y relates to Z, thus X relates to Z. To put it in a picture, it is like when X is bigger than Y and Y is bigger than Z. Thus, it makes X bigger than Z. We will now discuss symmetric, antisymmetric, and asymmetric relations. Symmetric relations. For all elements of X and for all elements of Y, if X relates to Y, then Y relates to X. Antisymmetric relations. For element of Z, if X and Y is an element of a relation and Y and X is an element of a relation, then X is equals to Y. Asymmetric relations. If X is an element of Z and Y is an element of Z, where XY is an element of a relation, then YX is not an element of that relation. Let's try this question. So, did you manage to identify the relations?
Part 2. Representation of relation. Representation of relation can be done using 0-1 matrices and directed graph. 0-1 matrix. Let R be a relation from A to B. The relation R can be represented by the matrix with row I and column J. It will equal to 1 if AI and BJ is an element of R, or equal to 0 if AI, BJ is not an element of R. For example, 1, 2, and 3 is an element for set A and set B, with R a relation between them. The element for relation R are 1, 1, 1, 2, 2, 2, 3, 2, and 3, 3. The 0-1 matrix that representing relation R. A1 and B1 is equal to 1 because 1, 1 is an element of relation R, while A2 and B1 is equal to 0 because 2, 1 is not an element for relation R. There are 3 Boolean operations involved: union, intersection, and composite. Example, union. Given set A and set B with R1 and R2 are the relation, find R1 union R2. First, represent R1 and R2 in 0-1 matrix. In union of two relations, it will always equal to 1 except when each element in both matrix is 0. Example for intersection. Given set A and set B with R1 and R2 are the relation, find R1 intersection R2. In intersection of two relations, it will always equals to 0 except when each element in both matrix is 1. Composite. Composite AB is the Boolean product of matrix A and matrix B. Example for composite. Boolean product A composite B is defined as each element in row A will intersect with each element in column B. Then the element of the intersection will do the union operation. Directed graph or digraph. Digraph, a set V of vertices or nodes, a set E of edges, ordered pairs of elements of V. For each AB, A is initial vertex and B is terminal vertex. Example for digraph. The elements of R is representing using directed graph. The arrow is used to display the graph. For example, 1 is pointed to 3, so the element of R is 1, 3.
For this part, I want to talk about relational database and n-array relations and its operation. N-array relations. Let A1, A2 to the AN be set. N-array relationship on this set is a subset of A1 cross A2 cross to the AN. The sets A1, A2 to the AN are called the domains of the relation and N is called its degree. So, what is a relational database? Database is a collection of relations. After that is structure of database. Database consists of tuples, tables, primary keys, and composite key. As a picture below, we can see that all the tables have their own primary keys and all the table is related to the other tables. So, what is tuples? Tuples is a single row of a table which contains a single record for that relation. For example, we see a picture below. We can see a table of an employee. So, the tuple is single record in that relation. For example, employee ID SN001, first name Amesh, last name Dubey, and salary 60,000. Table. Table is also known as a relation. For this example, below is table called customers or a relation called customers. In this relation or table, it has attribute which is customer ID, first name and last name, and it has their own record or we call it tuples. For this example, we have a database of customers whose records are represented as 3 tuples with the field customer ID, first name and last name. We can rewrite it like this. After that is primary key. Primary key is a domain of an array relation is called a primary key when the value of the n tuples from this domain determines the n tuples. Primary key must be a unique and cannot have the same value with other records. The function of primary key is to identify or to differentiate with the other record. So in this customers table, we can see that customer ID is a primary key. It is because customer ID has unique value and different with the other record. This is because primary key commonly only use ID number because it has unique value. Composite key. Composite key is a combination of domains that can also uniquely identify and tuple in an array relation. When the value of a set of domains determine and tuple in a relation, the Cartesian product of this domain is called a composite key. For example, in this table, student ID and enroll ID has a unique value. This is because composite key is a combination of unique attributes. Student ID and enroll ID are both unique, so they are composite key. After that, an array operation. First is selection. Let R be an array relation and C a condition that elements in R may satisfy. Then the selection operator SC maps the n-array relation R to the n-array relation of all n tuples from R that satisfy the condition C. For the example, Apply the selection operator at C, where C is the condition height in meters more than 1.6. So the question 1, height more than 1.6. So we can see that there are 3 records that state height is more than 1.6. Projection. The projection Pi I2 to the Im, where I1 less than I2 less than to the Im, maps the n-tuple A1 A2 to An to the m-tuple AI1 AI2 to the Aim, where m less than or equal to n. For example, what the result when the projection P1 and 3 is applied to these 4 tuples relations? So first we need to see H1 projection 1 and 3. So what does it mean 1 and 3 is it want a value from first and third tuples. So the answer is USM, UTM and Jackson CS. Join. Join is an operator to combine 2 tables into one if they share some identical fields. Let R be a relation of degree m and B a relation of degree n. The joint JP R and B where P less than or equal to m and P less than or equal to the n, and P is overlapping attributes. A relation of degree m plus n minus p that consists of all m plus n minus p tuples, where the m tuples belongs to R and the n tuples belongs to B. For example, here we have BMI tables and academic tables. So the question is, let R be a relation for BMI and S be a relation for academic. So what is J2, R and S? First of all, we need to find the similarities of attribute between these tables. So here we have student ID and name, which is same with the other tables. So we have to eliminate them to avoid the attribute be redundant. So once we join, we have student ID, name, course, CGPA, weight and height attributes. Since R and S has 4 fields respectively, the relation J2, R and S has 6 fields. This is because 4 fields plus 4 fields minus 2 fields, which is 2 where the similarities come. So it becomes 6 fields. So that's all for relational database and an array relation. Thank you.
Equivalence relation can be defined as a relation on a set A is called an equivalent relation if it is reflexive, symmetric, and transitive. Equivalence relations has 3 properties. First is symmetry. Symmetry is when A is equivalent to B whenever B is equivalent to A. Second is reflexive. Reflexive is when every element is equivalent to it. The last one is transitive. Called transitive if A and B are equivalent, B and C are equivalent, so that means A and C are equivalent. Any relation that satisfies all these 3 properties is called equivalent relation. Let's take a look at one example. Which of these relations on 0, 1, 2, 3 are equivalence relation, and determine the properties of an equivalence that are select. We can know that question 1 is equivalence because it is reflexive when we see every element is equivalent to itself. Question 2 is not equivalence because it is not transitive. In this relation we have 1, 3 and 3, 2, and it will become transitive if it have 1, 2, because we know that if 1 is equivalent to 3 and 3 is equivalent to 2, and then we must include 1 is equivalent to 2. This relation doesn't have that. For question 3, this relation is equivalent because it is reflexive like 0, 0, 1, 1, and it is symmetric like 1 equivalent to 2 and 2 equivalent to 1. So it will become equivalence relation. Next we move to the equivalent class. Equivalent class can be defined as let R be an equivalent relation on the set A. The set of all elements that are related to an element A of A is called the equivalent class of A, and it can be denoted by square bracket A. What it means that for each A in equivalent class, an equivalent class is a set of elements that are in A with the property that the element is related to A. So basically, all the elements related to A is called equivalent class. So we know that R is equivalent relation, and that means it is reflexive, symmetric, or transitive. So let's say that we have set A that contains value 1, 2, 3, 4, and 5. And I want a reflexive relation, so I take 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. And for the symmetric relation, we take 5 to 1, and we must take 1 to 5 to become symmetric. Then we take 4 to 3, and we include 3 to 4, and finally we take 3 to 2, and we must include 2 to 3. And for the transitive, we see that 4 can go to 3 and 3 can go to 2, so basically it means that 4 can go to 2, 2 can go to 4. And let's create an equivalent class, which is 1, 2, 3, 4, and 5. So first thing to do is we look what value is related to 1. So we get 1 and value 5. We look what value relate to 2, so we get 2, 3, and 4. And value that relate to 3 is 3, 4, 2. And value that relate to 4 is 4, 3, 2. And 5 is 5 and 1. So what we construct here is we get the value of each equivalent class. What we can see here is equivalent class 1 is same as equivalent class 5, and equivalent class 2 is same as equivalent class 3 and 4. So clearly that's when we union equivalent class 1 with equivalent class 2, we have set A, and when we intersect equivalent class 1 and equivalent class 2, we get empty set.